So thank you to come to our talk, Embedding AI. Don't burn your fingers in the AI movement, in the AI revolution, especially with the nice weather outside. So what are we doing inside, right? I'm Maarten Vandeperre. I'm Specialist Solution Architect for Red Hat, specialized in application development and AI. And with me, I have today Camille.
Hi, I'm Camille. Nice to meet you. I'm an AI solutions architect at Red Hat.
So today we'll talk about AI. And it's a bit like, ooh, AI. Everybody wants to play with it. And play with it is the correct terminology. Because whenever you want to put it in action and production, it more often looks like this. So what do we see? For example, Gartner came with some reports that mentions that a lot of AI projects fail to get in production, fail to get mature. What happens? Well, management most of the time sets unrealistic targets, and AI is often by management not seen as an implementation detail, but as a goal on its own. So we have to do AI for the sake of AI, not to solve some real issues. And next to that, I already mentioned it in the introduction, we've seen AI a bit too much as a toy and not yet as an enterprise product. So how can we fix this? That's what we are going to talk about in this talk today. And we'll start briefly with introducing some concepts, and then we'll go through some challenges that are happening and how we can fix these. So first, some concepts. Come here.
So thank you. Yes, so now let's talk about vectors. Has anyone have had some linear algebra classes in their high school or university? Very good. So you might be familiar already with the concept of vectors. So what is a vector? It's really a list of numbers which represents data in a simplified form. I have added here some visuals. Okay, very good, it works. So here there is the x-axis, which is, in our case, we have placed it to 10, and then we have the y-axis, which is to 8. So this is how the vector would look like. It's like this. So first the x-axis and then the y-axis. That's really what a vector is in a very simplified form. And here you have the so we have some vocabulary which is related to vectors. So the direction of the vector, right? Obviously, we have the tail of the vector as well as the head of the vector. You see here, this is the magnitude. This is how we call, I would say, the steepness of this. So this is now the vocabulary which we introduced about vectors. What's important to remember is when you see 10, 8, a vector being 10, 8, this is how it would look like. So you have two-dimensional spaces type of vector, so 2D, right? This is what we just saw. However, you can have 3D spaces vectors as well, or you should have, you can also have even very high dimensional vectors, which are perhaps a bit more difficult to be represented visually as well. Okay. So now let's look at some practical examples. So how can we use vectors after all? It was a nice class in linear algebra, but I want to find out what I can do with it, right? So the first example would be the customer satisfaction. So the x-axis is the revenue generated from the customer, and the y-axis is the customer satisfaction. So here you see 10, 8, as I mentioned before, 10 being the x, 8 being the y. The magnitude is this one. It's the overall impact. And the direction, what does this show is like how both factors influence each other. Now let's talk about another use case. How close are the cities to each other? How can we represent this in the vector world, I would say? So if one city is here and another city is at 10, 8, the city 1 it's at 0, 0, second city is at 10, 8, This is how you can represent this visually in this two-dimensional space vector. So why is this important for AI? What does it have to do with AI, how close cities are to each other? So it is important because we want to see how words relate to each other. We will talk later about this, but those are the fundamental concepts. Now, what are tokens? So tokens is a basic unit of text that really a model works with. So when you use ChatGPT, for example, or an open source version such as Mistral or Granite, then you input some text. The first step for the model would be to tokenize this text. What does tokenize mean? So it represents the chunks of the original data. So here we have added in the GPT tokenizer the text, some words. So many words map to one token, but some don't. It's indivisible. So example of a text, and here it outputs, we have detected 57 tokens, which is also the number of characters. Let's check the first line again after it's tokenized. Many words map to one token, but some don't, indivisible. So here you see that one word is equal to one token. The punctuation is equal to one token, but the token can also be a subwords, I would call it. And you see this is a two token. So this is an important concept to know as AI tokenizes. It breaks down the text that you input. What does AI do? I will also talk about this later, but essentially it has text, it tokenizes it, and then it represents it as vector, what we have shown before. So now, what's our challenge? What's our problem statement? We need to identify, search for similarities in between words and sentences, a concept known as similarity search. So here we have described 3 animals, dog, cat, and wolf. Let's perhaps start with the dog example. A loyal domestic animal known for companionship. We give this to the model, and the model tokenizes this. A loyal domestic animal known for companionship. What does it do afterwards? It represents those words as vectors. It takes the relevant words, so for example, loyal, represented as 09, 02, 03, so three-dimensional, domesticated animal, etc. Then the dog vector would look like this one, for example. Please keep in mind that this is a very simplified example. It's really to understand the concept because the concepts are the same. So here we have a table and we have dog. This is our knowledge that we have. So we have dog, cat, wolf. We have all tokenized the description. We have first given the description, then we have tokenized it. After having tokenizing it, we represent the relevant words as vector. So this is how our table would look like with the three animals. So then we input a query. I want to know which animal is domesticated, wild, and related to dog. What does the model do when it gets this query? So here you see the query. The query will go through the exact same process that I described. It will tokenize the query, and after that, it will vectorize. It will represent the words as vector, as we have shown. Once the query looks like this, what does it do? So it compares the numbers with the animal description. So it compares the vector of the query with the data that we have about the animals, with the vectors that we have as animals. So what does it do? It does a similarity search. It computes the similarity. There are different ways to compute similarities, But this is really how it does. So the closest answer to this, the top one, the most similar result to this would be dog. So dog versus query vector 0.98. As you can imagine, it's because in our query, there is the word dog. Then the second most similar is wolf. And the third most similar is cat. So you can choose, please give me the most similar animal. However, this can be a bit misleading because here this would be dog, but we want an animal which is related to dogs, but not dogs itself. So make sure that when you compute the similarity search, you don't choose top 1, but perhaps you can choose top 10 or top 5. Usually you have a much more bigger table. As I said, this is a very simplified example, but yes. So then let's quickly highlight hallucination. What could a hallucination be? So for example, I have this table with those 3 animals, dog, cat, wolf. This is the only 3 animals that I have currently in my vector database. And now I write a query. What animal can swim under the water? And perhaps, I haven't tried it myself, the model can return cat. However, this is not true, right? But the similarity, it would be the most similar to cats because this is the information it has. So yes, I wanted to highlight this is very important. Know the data that you have available before computing queries, before computing similarity search. So now let's talk about model biases. So you might have heard in the press every now and then, read in the newspaper, there are different types of biases AI models and humans from time to time can have. So for example, racial bias, education bias, social class, age, gender, and this is very dangerous, right? This can lead to very unfortunate outcomes. So, for example, let's say you train your model with the data of a specific forum that is very racist. So your model will end up racist. So this is a very dangerous thing that can happen, especially as we give more autonomy to AI nowadays. And we should be very well aware how AI models work and why do they come to this result. But sometimes bias can be useful as well. So for example, in the healthcare industry, some diseases, women are more prone to have some diseases than men. Older people can have other diseases than younger people, or are more prone to have certain diseases. Now let's talk about model drift. So you see the picture. There is one husky and one wolf. So what happened? And it was a very interesting case where a researcher, they developed a neural network model, a computer vision model, which was supposed to detect, is it a husky or a wolf? And after some time, they realized that it mislabels the husky as a wolf, the wolf as a husky all the time, and that it didn't work. And why didn't it work? So they had to go through their data that the model was fine-tuned on. They had to really research about this. And what did they find out? That actually, every time a every time a husky had snow, there was snow in the background in the picture of the husky. Every time this happened, that it would say, it's a husky, right? So all the training data was a husky with snow in the background, exactly. So every time it saw a wolf, which had also some snow in the background in the picture, then it would mislabel it. So that's a very interesting use case, and that's the classic example of model drift. You can have different types of model drift, so color scale, orientation, or context. So here we go. Let's go to the next slide, and my colleague will talk to you about Kafka.
Yeah, just two more technical concepts, and then we go to the real challenges. What we want to highlight as well is the use of Kafka. For the ones that are not familiar with Kafka, you can see it as an event orchestrator, messaging system, eventing system. We have producers that can put events, messages on the topics, and then you have consumer groups that group consumers or individual consumers that will deal with these messages or events. Service mesh, for the ones that are not familiar with it, you have an application landscape. The mesh will inject some proxies to all your application containers, and you will have control plane that will control the way how requests are coming in or going out of these containers, out of these applications. It has an added value that you can do advanced routing strategies and standardized mutual TLS enforcement, for example. So Kafka, the eventing system, service mesh, a layer on top of the application networking layer. An extra advantage with the service mesh is the different deployment strategies that you can do. For example, validating. It's a mirroring approach where you put the newest version next to the oldest one, and you start with mirroring the requests. Important to note, only from version 1, we do something with the responses, which means if you want to make use of the mirroring approach, you will need to have monitoring and logging in place to see how it's reacting. It will have its use cases in AI, but can be useful, for example, after huge refactors, where you can see how the application now deals with the resources, for example. Then canary releases and blue-green deployments to roll out stuff in production. Okay, why can it be handy as well in an AI space? Let me quickly open. This is a Jupyter notebook with which we can do some AI magic. If you want to hear more about the AI magic, we'll have a talk, Harry Potter style, at 5 o'clock today as well. And that one will be in French. So in this notebook, we will take an insurance claim, and we will extract information out of it. What happened, where did it happen, and when did it happen? And now we have Mistral as one of the models that is already in production. But we saw that we have a smaller model that we could use as well, that uses, for example, half of the resources. So it would cost less to have this model deployed. But we don't know how it would interact, so let's validate this. Some Python code, you have the prompts, you have the claim and the final prompt. So here you have the claim with an accident that happened. First one, it was not Mistral, it was the Granite one. Sentiment, very complete. Location of the event, yeah, you don't have to read through it. You can trust me that this is true. And the time as well. So this is the one that we have in production. It's working like we want to. Now with the smaller model, we say sentiment positive. Still okay, but not enough detail for use case. Location, yeah, this is the location of the garage, not the location of the accident. So it's a location, but it's not what we want to have. And time, normally it says a day. Now it's even completely wrong as well. So this model uses less resources, but it's not possible for us to put it in a production system. How does this relate to the service mesh? Well, the stuff I was doing now with the Jupyter Notebook, you can do this in a test environment with test data. But with AI, you have one big issue. And it's often you don't have the real data, the real-time data, the production data at your disposal when you want to validate stuff. So now with the mirroring approach, you can put a smaller model next to the model that you already have in production and see how it is reacting on your production data real time. And then upon these results, decide if you want to use it in production, yes or no. So first thing that you can already do is implement the service mesh to have these deployment strategies in place. Another challenge that you have is tools. You have a lot of tools on the application landscape in the Kubernetes world, and nowadays in the AI landscape as well. To give you an idea around Kubernetes, this is the CNCF landscape, so the Cloud Native Grocery Store, as we name it. And this is already what you need to monitor to get Kubernetes at an enterprise-grade level. Then, nowadays, we have tons of extra components to enable AI in Kubernetes. To showcase how big this environment is, we've hidden a Wally in the screen. I think it's a bit too small to read it, but slides will be shared afterwards. If you don't want to know where he is, close your eyes for 5 seconds, because we didn't trick you. He is in the image. So with these tools, that's the only marketing slide I will have for Red Hat. What we do is we use all these open source components, upstream components, integrate them for you and harden them, so that you have to think less about all these minor components that you need to integrate together, and you can already go with a mature enterprise-ready platform to start from, and you can start extending with real innovative things. You don't have to reinvent the wheel then. Okay, next to the tools, management often expects us to build the entire AI embedded component in one go, in one big bang. But this is not how it should go. And for this, let's maybe take a little detour and go to gem mining. How does that work? Well, you sit next to a river, you take some water in a basket, you filter out the rockets, and then you filter out the rockets that have, for example, some gold inside. You extract the gold, and then you make it in a product, which you then productize, sell. But what has this process now to do with AI? Well, if you put this in schema, and we think about how AI works, well, it's entirely the same schema. You start with the water, which is the raw data. You go to the rocks, the collected rocks structure data. You have some business insights on it, or you want to get some business insights from it. You train a network on it into the model that can be deployed. And how can you now go step by step to mature AI implementations? Well, you shouldn't rush. You should make clear that the foundations of AI should be stable. And it all already starts with a stable application landscape, an agile application landscape. Because, for example, if your data scientists want to have a new weather API embedded, and you're working in release cycles of, for example, 6 months, no way that he would be happy with the answer. Wait for it, in half a year, the API will be there, and you can do your stuff again. Second step is go to structured data. Go to other databases, which is important for a reason I'll come back to in a second. And then here you can already have shortcuts. From the structured data, for example, graph database, in a file system that's feeding Spark cluster and Hadoop cluster and so on, you can already introduce first-day intelligence. It will be hard-coded intelligence, for example, graph queries, graph database queries, but you already have intelligence from day one, which can be deployed. And sometimes already sufficient for the use case that you have. And then in the next step, the third step, you can go all the way and embed AI ML into your landscape. Now we have the models, but nowadays, besides the big ones, no company, no organization will be building its own model. We will be starting from foundation models. But how do we enhance them? With our data.
So, now let's talk about model enhancement. Has anyone of you heard of RAG, the concept of RAG, Retrieval Augmented Generation? Okay, yeah, I would say more than half of the room, let's say 80%. That's a lot. Yes, we hear this word everywhere nowadays. So now let's talk about what really is RAG. So RAG is short, as I said before, for Retrieval Augmented Generation. So we augment the knowledge of the model. How do we do this? Let me go through it. So first, the user gives a query, and the query would be, why is Camille's cat, Mitsu, the cutest cat in the whole world? And this query, we send it to the application. The application would then search relevant data and documents to the knowledge base. The way it searches for it is most of the time is doing a similarity search with the vectors, what I mentioned before. And it then returns the relevant data and the relevant documents to the application. So how would we generate a response? The model needs three things: the prompt of the user, right? Why is Camille's cat the cutest cat in the world? The query, as well as the relevant data and documents. So this will go to the model. This model can be an open source model, such as Granite, Mistral, or a closed source model, such as GPT, for example. It will then go through the model and generate a response. The response output can contain citation as well as some reference needed. So for example, it can say, it is the cutest cat in the world because she loves cuddling. And this goes back to the application, and then it goes back to, then the user can read the response. In a nutshell, this is what RAG is all about. So it's not the same as fine-tuning, which I will talk after about this, but it's a way to augment your knowledge. Now, let's talk about something else called function calling. Has anyone heard of function calling? I'm actually curious about this one. Okay, I see less hands up. Okay, very good. So now I will explain the basic concepts, which is behind function calling. So the user asks, what is the weather today? So if you ask this to a model which does not have access to internet or to outside sources, it will output the wrong response because it has been trained on past data, on historical data. So the query goes to the main application, and then it sends the prompt with all the available functions. So one available function could be check the weather API of Luxembourg. This then goes to a model, as I can say before, can be an open source such as Mistral or Granite. And if the response requires function call, the LLM responds with the function definition. This goes back to the application. And then there is the function execution, right? You fetch the data of today's weather, for example. And this gives a response back to the application. Then the application sends this data, which could be perhaps a JSON string, a JSON file, which then goes to the model again. The model can then create a nice response. Today's weather, it is sunny, there aren't any clouds, it's very warm, and the final response is then returned to the application and the user can read it. So this is what is behind function calling. We then have fine-tuning. I will quickly mention today an open source project which is called Instruct Lab, and this is, I would say, fine-tuning for everyone. You can fine-tune a model on your servers, on your local machine, on your MacBook, especially if you have the M series, it works pretty well. And what it does, what is fine-tuning? Fine-tuning, it retrains the model with your own data. And with Instruct Lab, you can do this using this open source library. It generates synthetic data, and then it retrains with your data set as well as the synthetic data it has generated. If you are interested, I invite you to Google it, and then you can read the GitHub page about this. There are more details. So we would also like to advertise our next talk, which is at 5 p.m. Yes, at 5 p.m. We have a talk with a bit more playful theme, a Harry Potter theme, and there we will talk about the world of agentic AI. So if you have a interest in this subject, please go ahead and join us. Just as a heads up, the talk will be in French and the demo will be in English, so it will be a very bilingual talk. It will be no problem. It will be a very bilingual talk, just to let you know. Yes. And here you go.
Okay. Sovereignty. I think nowadays it's a hype, buzzword as well, to have sovereignty, sovereign AI. But next step, I want to introduce as well lack of dedicated environments. And what do I mean with this? When I was working at a big data company, we provided data APIs to the applications, to the business, but then we had data scientists as well. And they were not happy with the API landscape. Why? API landscape development followed the Scrum agile cycles, so it was too slow. And they didn't want to use the APIs, which were then paged and all these things. They just want to have their raw data in CSV files. So all with sovereignty, you need to have dedicated environments where you can store confidential data, for example, on-prem, and scale out to cloud hyperscalers, or you just want to have different environments for different usage perspectives. If you want to do this, it's important that you use an underlying infrastructure that allows hybrids or multi-clouds. Kubernetes and with extent OpenShift is, for example, a technology that you can use to accomplish this. Another thing is, as I showed you already in the 3 tiers of roads towards AI, that if you have the application landscape stable, that you should think about a data landscape, data foundation. Why? In the red part, you have the application databases and the APIs that you can use. But most of the time, that's not sufficient for your AI use cases. You will use, for example, governmental data, third-party data from third-party APIs. The blue ones over here. And this all needs to come together in these environments on which your data scientists work, on which your models get fine-tuned or maybe embedded in RAG use cases. So what you need over there is some kind of data layer that copies data to the new environments, and it keeps this data in sync that you don't have data corruption. An example implementation is, for example, with Kafka and then Debezium as a Kafka connector, who listens to changes on a database, pushes these changes to a Kafka topic, and then you have the consumer groups on the integration layer that can take these messages and transform it into or read-optimized database like Elasticsearch, for example, or real full-fledged data lakes, data warehouses. Another one, model flexibility. It's one that you shouldn't underestimate. Because myself as well, I like to start with proof of concepts on OpenAI, for example. But the big issue is, or one of the big issues is the EU AI Act. It's a good thing, it focuses on data privacy, but it can mean that one of the models that you're using nowadays is not allowed anymore in, for example, half a year. If you then hooked up to that model, yeah, you're screwed. It can be that your entire application landscape goes down if you're really heavily depending on this model. Other things is, for example, copyright cases. If they come into the picture, it can be that the model is not allowed anymore as well. So that's the regulatory stuff. Then it's better to have control that you can switch models if you want to. But next to that, you have every day new versions of models as well. So that can be handy that you can change these models as you wish, and maybe include a service mesh to validate if it really brings added value and that it behaves like you want to. An example of where it can be handy is, for example, last year in May, I was asked to check or to build an LLM that could transform one old programming language to Java. By then, there was no LLM available that understood that programming language. I started fine-tuning an existing one with InstructLab, but my background is software engineering, not a data scientist, so I was struggling a little bit with it. But then around August, Mistral came with a model that understood that programming language. As my environment was fairly flexible, I could just switch to the one from Mistral, and I didn't have to do this myself anymore. Another advantage of having model flexibility. Third one is that you're as well in control about your data flows around the model. If you have a chance, you can, for example, have a look at Stefan Jansen's talks about the Voxxed Genie plugin for IntelliJ. Main reason behind this as well that you can use local models, that you don't have to send all your business data to cloud AI models, because you never know what's happening with that data too. For this, yeah, the last marketing slide I have, but two things important. With Kubernetes and OpenShift, you can run everywhere you want to. You can run almost all open source models, but the two biggest components that you should take from this slide is VLLM and LLMD, which are two open source community projects. VLLM is an inference server, which is quite strong and compressing algorithms to reduce resource usage. And LLMD is a new project that allows you to make full use of the GPU infrastructure under your application platform. So yeah, I already mentioned this. Service mesh can be handy to validate if the new model is really what you want to have. Then model security. I think who is familiar with the concept of jailbreak? Okay, not too many people. Jailbreak is that you let an AI model do something that's not supposed to do. For example, try to get out the healthcare data from the people upon it was trained of. Then it is important that you collect or choose the perfect model enhancement methodology. For example, with RAG, you can protect this data, these data sets, with role-based access control, while if you choose for fine-tuning, the data is in the model. Then, for example, extracting it is already jailbreaking. But jailbreaking goes beyond this as well. For example, if you get access to the cluster and you start sending a lot of requests, you can DDoS the model, because in the end, it's a heavy monolith. So you should be protecting this for the internal DDoSing as well. And how can you solve this? Well, the service mesh with the advanced routing techniques can help there. For example, you can have UI components. UI components are linked to the internet, so are vulnerable for hacking. But whenever a malicious person accesses the UI components, he's through the service mesh not able to go to the AI model. He always has to go to a backend model where you, for example, have guardrails implemented. Next to that, with the mesh, you have already throttling available, so you can avoid DDoSing of the model from the UI component as well. So service mesh, even if you're not working with AI model, it's a great tool to introduce in your application landscape, because in the end, what's, for example, the difference in between an AI model and a database? They all have to be treated the same. They're all valuable components, of your infrastructure, and you should really protect them from malicious use. And then, if you have a cartoon-like drawing, these are a lot of personas that play the AI game. We're starting with developers, then data engineers, data analysts, data scientists, platform engineers, which can as well be security engineers, infra people, ops people. You have the functional people, you have the testers, and so on. If you put it in a more formal slide, it looks a bit like this, but you have a lot of personas playing together. And that's then important that you have looked, for example, on platform engineering to bring them all together in one ecosystem, that are not fighting silos, but it's just one organism within your organization that works together. Where does platform engineering come from? Well, if I only focus for the moment on dev and ops, in your imagination, you can already put the other pillar of data scientists next to it. Then you had happy devs in the past, because you only need to write code. Then they build it, and then they threw it over the wall, and ops people would take care of it. Ops were not that happy. Then with the rise of the cloud, it was a shift left movement. Developers happy because we got now the flexibility that we wanted to have. We could do everything. But management understood that message, and they pushed everything to us developers as well. So what you had now is overloaded developers because too many responsibilities, and confused ops people, because if you have the Amazon console and you open it, for example, to a developer, upon which where do you have the responsibility for the developer, and where starts the responsibility for the ops people? And that's something that platform engineering wants to solve. With platform engineering, you create a team preferably a team that contains and developers and data scientists and ops people and security people all together to build a platform. Now, it's important that they all come together. It's not just dedicated people. Well, if you have senior developers, for example, from the dev team as part of the platform engineering team, they know the struggles of developers. So you're building a platform for developers. If you're just building a platform and pushing it, adoption rates will be rather slow and low. On the other hand, these developers that are part of the platform engineering team can act as advocates for the platform itself, hence driving adoption. And on the other hand, the ops people that can build everything together, integrate everything. Security people think about, hey, you should do this and this, or it's best practice to not do this. And then they come all together. And then I can show you how it looks like as well. If you then put a portal on top of this, for example. Are there people that are already familiar with Backstage? No? Okay. Imagine we have the application platform. It can be OpenShift, can be any Kubernetes distribution, for example. We have some CI tooling. We have some CD tooling, for example, Argo CD. We have a service mesh in there and some logging monitoring components. Well, cool. It's already all integrated for us, but it's still a nightmare to work with it. We call it the bookmark hell, because when you start with it, you have 1,000 pages of documentation that you have to find back. You have for every repository a CI or multiple CI pipelines and a couple of CD pipelines and so on. On top of this platform, you could use a portal like Backstage to bring everything together, and which is then your single point of contact with your platform. Like, for example, this one is. And here the advantage is that you then can create abstraction layers, blueprints, like software templates, to bootstrap applications in a standardized way. The application will then be bootstrapped to a new GitHub repo, and from there on, you can tailor it like you want. How is this handy in the space of AI? Well, let's say, for example, we want to have advanced chatbots with an LLM behind the scenes. Then we can go for the software template, the blueprint of the chatbot. We just select some metadata that will be injected in the blueprint, for example, package names. Our AI team has delivered 3 models that we can use for this use case. We opt for Mistral, an image repository to put the images inside, and then a Git repository to push the final repository data to. If we now push it, then this chatbot application will be created in GitHub. We have some deployment configurations in this template as well, so we will have Argo CD working and deploying it already to OpenShift. You see, it's now fairly easy for developers to get started with the AI landscape without having them to know which deployment strategies they need to use, how they need to deploy a model, how they need to link the model to an application. They can just start from second one with the development and business needs. If you want to know more about this, we'll touch it as well in the talk at 5 o'clock. Oh, that was a talk for 5 o'clock. Okay, so what happened? We had way too many tools, and we still have, especially now with AI. You can solve it with platform engineering, internal developed platforms. Think about Kubernetes, think about OpenShift. We had big bang solutions, ask for management, but you can do it step by step. Another practical example here is, for example, we had to sometimes have to RFPs. Is that customer ask for, what can your tool do? Then they said, yeah, we need an RFP tool in AI. It can answer this, that we have to validate this. Yeah, okay, but it takes a while to build this. Well, in the end, if you just gave us a tool that's a UI on top of a vector database, like Camille explained in the beginning, that already returns to me the most relevant paragraphs of all the documentation we have. Yeah, I think I'm smart enough to read through 10 documents, for example, and then formulate an answer on it. In the second phase, if needed, because most of the time it isn't, you can put an LLM behind the scenes. So start small and do it step by step. The model enhancements we talked about, data and AI sovereignty, it will be more and more important, especially if you see what can happen in countries like the United States nowadays. Model flexibility, again, important there for the capabilities and regulation-wise. Model security, model deployment strategies, and bring together the different personas with platform engineering. So as the last slide, in Belgium, we have already had a famous cook who always ended his talks with, what did we learn today? So AI is way more than machine learning. It's an entire ecosystem now. You'll need an agile application platform, a solid data platform. Think about the deployment strategies and how to protect the models and monitoring, for example, for bias and drifts. And we, from Method, are there to help if needed. If you want to read something with a glass of wine or beer in the sun, there are some blog posts that you can read, and we have a GitHub repo as well where you can find all the information we talked about today. And with this, I would like to thank you for the attention, and feel free to ask questions. Some questions? No.
No question?
Go ahead.
Okay, first of all, thanks for your wonderful presentation, both of you.
Thanks.
Okay, just one question about the easy way to create application with the backstage stuff. Did not if it's available just on Red Hat environment, you have everything's in the cloud as usual, or you have to do this in premises if you want? What I'm talking about.
There, the answer is depending on what you're talking about. Backstage itself, it's started from Spotify. That needs a Kubernetes engine to run on because it's making use of Kubernetes APIs. But everything that you integrate to it just needs to have APIs. It can be on VM, can be on Kubernetes, can be on OpenShift, it doesn't matter. It's just a portal on top of APIs that brings everything together. Can be outside Kubernetes, but Backstage itself requires Kubernetes to run. Other questions? No. Okay, thank you.